Okay, so we are going to start our units 11, talking about waves. The main type of wave we're going to talk about are mechanical waves, but there are two different types of waves. There are mechanical waves and there are electromagnetic waves. Mechanical waves need a medium to move through. Electromagnetic waves do not. They can use a medium to move through, but they don't have to. And we're going to talk about what a medium is and the different types of mechanical waves today. So here are standards. You can pause that if you want to take a look at it. We're going to do our I can statements. So the ones we're going to actually go over today are the first three. We're going to identify the basic characteristics of a longitudinal wave and also the relationship between a period and frequency, and explain the relationship between velocity, frequency, and wavelength by calculation. So that is what we're going to focus on today. We're also going to talk about velocity, frequency, and wavelength, and talk about this a little bit, but we're going to focus more on the first three today. All right, so the agenda today is the parts of a wave, the two types of wave, calculating speed of a wave. Now this is a basic wave diagram. There are two types of waves as far as how they move. One is called a transverse wave and one is called a longitudinal wave. Well, right now, this is a basic diagram of a transverse wave. You are going to need to know the parts. So this is the height of a wave. This is called your amplitude. From one crest to the other or one shroud to the other is called a wavelength, the length of the wave. The very top of a wave is called a crest. The very bottom is called a trough. And this is your origin. Okay, so when you're calculating an amplitude, it's from the origin to the top of the wave or the origin to the bottom of the wave. Okay, so these are some parts you're going to need to know. Now, mediums. I told you before that a mechanical wave needs a medium to travel through, unlike an electromagnetic wave, which does not. And when we think of electromagnetic waves, we think of light, more light waves, radio waves kind of thing. These are a lot more like ocean waves and sound waves. That is what more of mechanical waves are. So the medium is a substance through which a wave travels. In ocean waves, the water is the medium. In sound waves, the air is the medium. Mechanical waves cannot travel through a vacuum. So a good example of this is outer space. Sunlight, which is electromagnetic waves, can travel from the sun to the earth through a vacuum, which is outer space. But sound waves cannot. So you cannot hear a sound wave in outer space. The only time you can hear sound in outer space is if you're using little microphones and projecting it through that way, like the astronauts do. But like talking, you can't hear sound waves in outer space. Okay, so it is important to understand that wave does not carry the medium; it only moves energy through the medium. Okay, so the mediums that it can travel through are solids, liquids, and gases. All of those can act like mediums. And waves travel throughout a rope when you shake one end of it. Therefore, rope is a medium. Okay, so it just depends on what the wave, the energy is moving through. And that's what a wave is. All right, so this is actually an example of a transverse wave. Okay, I'm going to show a video in a little while that actually shows these waves in action, which makes this a little easier to understand. A transverse wave it moves at a right angle to the medium in the direction, right angle to the direction of the wave. So this wave is moving this way. Okay, they move this way. They move at a right angle. Okay, when you see the video, it'll make a little more sense. But a transverse wave will always look like this. You'll see these big, long up and down lines. This is a transverse wave, okay? When you see a longitudinal wave, it looks very different. You do, however, need to know, again, the crest is at the top, the trough is at the bottom, the wavelength is from one to the other, and your amplitude is from the origin to the top or the origin to the bottom, okay? All right, so here are some definitions of the same thing that I just talked about. Wavelength is the distance between a point on one wave and the same point on the next cycle of the wave. This is easier to see when you have crests, troughs, amplitudes, and you go from one point to the same point. It's a little harder when you go all the way this way, but its wavelength is the wave to the wave, okay? Trough is the bottom part. We just talked about that, the lowest point on a wave. Crest is the highest point on the wave. Amplitude is the max displacement of the medium from its resting point, which is this line here, corresponds to the amount of energy a wave carries. Okay, so this is your amplitude. Okay. Now, a period is the time required for one cycle, a complete motion that returns back to the starting point. Okay, so this is a period from here to here. It's kind of the same as a wavelength, but it's not a wavelength. Okay, it's a different type of definition. Okay, it's one cycle from one wave to the other. The number of these cycles equal its frequency. So frequency is the number of wavelengths that pass a fixed point each second, measured in hertz. So when we look at frequency, when you have something that's moving faster, its frequency is going to look like this. Those little lines are going to be very close together. And then your wavelength gets shorter. Okay, so there's a correlation between frequency and wavelength. So as your frequency gets faster or higher, your wavelength gets smaller, and vice versa. When your frequency gets farther away, your wavelength gets longer. Okay. All right, so here's the first video. Hopefully it will play. Oops, maybe not. Oh, there it goes. All right, so let's watch the first video.
Ever seen a Mexican wave at a sporting event? The effect is a pretty cool display that goes all around the stadium, but no one has had to move seats. All waves can transfer energy from one place to another without transferring any matter. This is done by a series of disturbances or vibrations that carry the energy. Just like the people in their seats, only moving up and down when it's their turn. Waves can transfer energy through solids, liquids, gases, and empty spaces, otherwise known as vacuums. There are two types of waves, which we look at in more detail in another video, but the basic features are the same. These four words describe different properties of waves. Let's discover what each one means. The frequency of a wave is the number of complete waves passing a fixed point in a given amount of time. This time period is usually 1 second. This is what one complete wave looks like. So if this was our time period, the frequency would be 5. Frequency is given the symbol F and is measured in units called hertz. Hertz measure how many complete cycles per second. So how many people in our Mexican wave stand up every second. The frequency and period are often confused. The frequency refers to how often something happens, whereas the period refers to the time it takes to happen. The period of a wave is the time for one complete cycle, so the time taken for one person to stand up, wave, and sit down. This would be measured in seconds. When something happens repeatedly, we say that the event is periodic, and refer to the time for the event to repeat itself. The period of the Earth to orbit the Sun is 365 days. The period of a day is 24 hours. The period of a typical class at school is 45 minutes. Now for wavelength. The wavelength is the distance between a point on one wave and the same point on the next wave. For example, 2 peaks or 2 troughs. Wavelength is given the symbol lambda from the Greek letter and is usually measured in meters. Wavelengths can vary hugely in size. X-rays are very short, visible light is here, and FM radio waves are much longer. So we've looked at the frequency, period, and wavelength so far. Let's finish with amplitude. As waves travel, they create disturbance. The amplitude of a wave is the distance from the maximum disturbance to the undisturbed position. Think of a very flat sea, and then an incoming wave. The amplitude is the height of the top of the wave from the flat sea. Can you add the labels to these waves and work out the frequency? Notice that the top one is distance and the bottom one is time. Pause the video, work it out, and click play when you're ready. Did you get them right? In another video, we'll be looking at wave speed equation and connecting wavelengths and frequencies. For now,
All right, so that was a little bit more of a picture version with animations, which makes this a little easier to understand. If we were in the classroom, I'd be using a Slinky to show you the difference between the waves and all of that, but we are not, so we have to go with what I have. All right, so a longitudinal wave, we talked about transverse waves. Those are the ones that go like this, and you can see each individual wave. Looks like ocean waves. The other one is a longitudinal wave. And this is matter vibrates in the same direction as the wave travels, parallel. Now, these waves are a little harder to understand until you actually see them in motion. So I'm going to show you another video on the difference between transverse and longitudinal waves. This one has compressions and rarefactions, okay? And this one I love to do with the Slinky because I can hold it, make it move back and forth, and it's a really good demonstration on how this one actually moves. So I'm going to show a video again. However, let's look at the parts. This is a compression. It's when the waves are very close together, okay? And then this is a rarefaction. It's when they are separated out like this, okay? A wavelength is actually one compression to the other when it comes to a longitudinal wave. You do need to know that this is called a compression, and these open long areas like this one too are called rarefactions, okay? Now, so a compression is the area where particles in a medium are spaced close together, and rarefaction is the area where particles in a medium are spread out, okay? And this whole thing is going to move, and I'm going to show the video because it's much easier to see it with the video. So let's watch the video on transverse and longitudinal waves.
Waves transfer energy from one place to another. You should already know how to describe them in terms of frequency, wavelength, and amplitude, which we looked at in another video. In this video, we're going to look at 2 ways they can be classified. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is traveling. Notice that the ends of the Slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the Slinky, but the wave itself moves from left to right. So the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy, also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it. It's just the energy that moves along. Transverse waves are usually used to show the wavelength and amplitude. Pause the video and see if you can remember how to label the amplitude and wavelength on the diagram. Did you get them right? The waves on the surface of water are transverse waves. They make the water surface go up and down. All types of electromagnetic waves, like visible light, are also transverse waves. So, now you should be able to describe the differences between transverse waves and longitudinal waves. Remember, it is the energy and not the slinky itself that travels.
All right, so I think that's a really good video, and I don't have a slinky I can show you in a video, but I think that's a really good video on how to distinguish between a transverse and a longitudinal wave. Now, there's one more type of wave that sometimes is given its own classification of a type of wave, which is a surface wave. And this travels along a surface separating two mediums. Most common are ocean waves. So this is basically separating, water, the air, the water, the ground. So it's separating two medias. They're called media instead of mediums. But they travel along a surface separating two medias. And most common are ocean waves. Okay, so that's our third type of wave. All right, so let's do a review. Which of these does not create waves? Water in the ocean, sound from a radio, light from the sun, rain from the sky. So we look at this, we've already talked that ocean waves are waves. Sound are longitudinal waves. Light from the sun is electromagnetic waves. So the only one that would not be would be D, rain from the sky. That's precipitation. All right, what is the one thing that describes the motion of all waves? It's always fast. Now, we talked about frequency. Sometimes it doesn't move that fast. It always repeats. Waves go over and over and over again. So I think that could possibly be the answer. It's always slow. No, it starts and stops. Starts and stops, but it goes back the other way usually. So I would say this would be our closest answer. It always repeats. What is the top of a wave called? Do y'all remember? It's the crest. And what do you call the measurement from the top of one wave to the top of the next? Remember this? From one top to the other top, or even from one bottom to the other bottom. It's called a wavelength. Remember, this one here is your amplitude. And peak doesn't actually apply, and neither does pattern. Okay? What is the measurement of a wave's height? Oops, I just gave you that answer. It's right here. Amplitude. Okay? So those are a little bit of a review. And there's the answers. All right. So the next thing we need to know how to do is calculate the velocity of a wave. You do need to know how to manipulate this equation, and it does have a triangle, which makes life a little easier. So we're going to draw our little triangle. So V equals lambda F. Now, this symbol is for wavelength, so don't get confused. So lambda, this is wavelength. Okay. And I just spelled that wrong. Sorry. NGHTTH. Okay. And the F is for frequency, which makes it a little easier to remember, but lambda tends to make a few confused. And we already know that velocity of a wave, velocity is signified by a V. So we're going to just use V in this, but you know it is the velocity of the wave. That's why they have the subscript of a W. We know velocity is in meters per second. You now know that wavelength is length, so it's going to be in meters. And frequency is going to be in hertz, okay? Because you hear a lot of times when we're talking about sound and hertz, how many hertz do you need to make this amp work? So those are some words you need to be familiar with. And this, of course, is our triangle, and we're going to use it for the next couple of problems. So let me draw my triangle again. So we have velocity equals lambda f, okay? Just remember this one is your wavelength. It'll take a little getting used to. The other is frequency, not hard because it starts with an F. And then V is velocity, which is your speed of your wave. So we know that if we're trying to find what is the speed, it's going to be this one. Okay? And it could be F the other direction too. It's multiplication. It can go either way. So we're good. So it says one end of a rope is vibrated to produce a wave with a wavelength of 0.25. So wavelength is your lambda. So we're going to do wavelength is 0.25 meters at the frequency of 3 hertz. Hertz is like this, capital H, little z. Okay, so we're just going to put it in the equation. So we're just multiplying. So we're doing 0.25 meters times 3 hertz. And you can pause it if you want to try it yourself. Use the calculator. If not, the answer is 0.75. Velocity is always in meters per second. So here is your answer. All right, so that one's pretty straightforward. You just plug the numbers into the equation. This one might confuse you a little. Lambda is for wavelength. And let's do one where we actually have to change things around. So again, we have our triangle. V equals lambda frequency. Okay, so let's put it in. We got V is 280. So when we're trying to find wavelength, so we're just solving for this one, you cover, I can't really cover it on here, but you cover this one and you use these two. So lambda equals V divided by F. Okay, so we're going to do 280 meters per second divided by 5 hertz. And if you calculate that out, you should get 56. And wavelength is always in meters because it's length. Okay, so that should be our answer. So these are pretty straightforward, like we've done before. You just use your triangle to figure out which part you're solving for. Just make sure you remember that this means wavelength. Okay, the other two are pretty easy to remember. F for frequency, V for velocity. All right, so let's do another example. We're looking for frequency. So if I draw my triangle, and we have V equals lambda F. You cover your F. Can't really cover it here, so I'm going to do this. Then it's V divided by lambda. Okay, so we're going to plug our numbers in. F equals 98 meters per second divided by 30 meters. And when you actually multiply that, I'll give you a second if you want to pause it. You should get 3, and we're going to round it because we have 2 numbers on each of the numbers that we're calculating together. So I'm going to round it to 3.3. And the units for frequency is hertz. All right, so you have a couple of assignments today because I need to first review the parts of the wave. So you're going to have a quizzes. Then you're going to do our calculation sheet like you've done before to fill in. And I'm going to have one extra assignment to prepare for Monday, which is an Edpuzzle on the types of interactions of waves. All right, so if you have any questions, please let me know.